Welcome back. In our last video, we considered extensively the derivation of the Laurent series. Now we will take an example on Laurent series. In fact, we'll take a couple of examples on Laurent series, some of which we would take in full, and some of which would also leave a little bit of for you to also practice on. Now, this is very, very interesting and important. Why? Because it would set the stage for your evaluation of any and every kind of function to which you have been asked to find their Laurent series expansion. As always, make sure to like, share, and subscribe, and turn on notifications so you do not miss any of our videos. Let's begin. Now, the very first thing you need to know when it comes to the Laurent series is, number one, the biggest tool you are going to be utilizing in solving your expansions is you're going to first and foremost start off with a good use of partial fractions. Partial fractions are going to be very, very important when it comes to calculation of Laurent series. This also talks to the reason why we want to take as many examples as possible so that we can show you as many variants of partial fractions that we have. So this would sort of help you cover a review of what partial fractions are. Now, once you've been able to carry out the partial fraction representation, the next thing would now be for you to be able to identify the discontinuities or the poles, right? We would still have a video coming up where all of these terms, poles and the singularities, will be extensively explained. But for now, we just have to know that these poles just refer to points of discontinuities where the function would be undefined. Now, let's begin with a simple example. We would say, so let's start off with this. We have to find the Laurent series expansion of 1 divided by z into z minus 1, and we have to state their region of validity. This is what we have. Now, based off this question, the first and most important thing we want to first and foremost clarify is, number one, in this case, the regions of validity is either, number one, given to you in the question, which is your permissible region of validity, or the question will ask you to figure out the region of validity yourself, which is what we have in this case. Now, if the question provides you a permissible region of validity, what happens is that it means that whatever region your question or your problem set has put forth, you would have to limit those regions based off the permissible region that has been provided to you. That is the very first thing to keep in mind. Now, once we have that, the next bit of business is how then do we find or determine those regions if we are not given any pointers at all? So let's see. Now, for this question, remember, the very first thing we want to do is to express the partial fraction, right? Now, the partial fraction bit is pretty straightforward. There are some rules that guide the expression of a fraction into partial fractions, and one of those rules states that if you have a denominator that have distinct factors, which means they have been factorized into distinct forms, you can split up each of those factors as a simple fraction, like so. Now, because these distinct factors here are linear factors, which is they have powers of 1, the degree is 1, the numerator would be constant variables, right? So would be constant parameters. That's a better way to put it. So we have a divided by z plus b divided by z minus 1. So because we have linear factors here, the numerator took constant parameters. If we had quadratic factors here, the numerator would take linear parameters. So whatever your parameters on top would be one lesser in degree compared to whatever you have as your denominator in terms of the factors. That is very, very important. Now, how do we carry out partial fraction? The very first thing is we take the LCM. We would be as explicit as possible in solving this question so that I can formulate a basis for the other parameters as we have. You can take a minute to solve for A and B and give us your answer. So we have an idea of what exactly you got prior to continuing the video. So once you've done that, you can then hit play and then continue watching the video to see our solution. Now, we've taken the LCM. The next thing we do is cross multiply, which would immediately mean that the LCMs will cancel out, or the denominators will cancel out. We'll then have A into Z minus 1 plus BZ equals 1. Now, when it comes to finding these constant parameters, there are two major processes you can use. You can either use what we call the cover-up method, or you can utilize what we call the comparison of coefficients. The cover-up method works very, very accurately, especially when you have distinct factors. In this case, we have distinct factors Z and Z minus 1. Now, the process for cover-up tells us that we would set one of the factors to 0 such that we would obtain a result for Z, and then we would go back to the equation and set in the value of Z. So in this case, we have A into 1 minus 1 plus B times 1, which will be equal to 1. 1 minus 1 is 0, so this would immediately mean that B is equal to 1. Then we'll move to the next factor, which is Z. So we just set that to 0, and Z will be equal to 0. And then we'll then have A into 0 minus 1 plus B into 0 equals 1. And this would immediately mean that A will be equal to minus 1. There we go. So A is minus 1, B is 1. I hope this matches what you also got for your solution set. Now that we have this, we will then go back to have 1 divided by Z into Z minus 1 to be equal to. Now remember, the same way you split your partial fraction should be the same way you return the constant parameters into it. So you have A over Z, that would become minus 1 over Z, and then B over Z minus 1 will be 1 divided by Z minus 1. This is what you're going to have. So this shows extensively how to solve partial fractions. So this is a bonus for you in order to help you solve other kinds of Laurent series. Now that we have this, partial fraction is done. The next thing is to determine poles. Now, in determining poles, we have said that the poles simply refer to points of discontinuities, which is the points that make the function undefined. All we just have to do is set the denominator of the function to 0, as always. Now, we set it to 0, it means that we'll have that Z is equal to 0 or Z is equal to 1 are the poles. These are the possible poles. Now, once we have determined the poles, which are the discontinuity, which are the points where the function becomes undefined, because if I put Z equal to 0 here, I have 1 divided by 0, that's an undefined function. And if I put Z equal to 1, I will also have 1 divided by 0, which is still undefined. Now that I've determined the poles, the next thing is to now determine my region of validity. Now, how exactly do I do that? My region of validity is going to be determined on the radius on those poles, right? Remember, those poles are complex numbers, which means they would have their modulus values. Now, I would determine a region of validity based off the modulus of those poles. Now, how exactly or what exactly do I mean? Remember that the radius is, of course, a positive result, a non-negative result if you so wish. So it will start from 0 and, of course, end to infinity. That's what we have. Now, this region or this range of values for the modulus will be divided or will be cut at those poles or at the modulus of those poles. Why? Because remember that those poles cause the function to be undefined. So we want to make a split at those poles so that the function remains defined on every other place. Remember, when we determined or when we stated the Laurent series, remember we said for Z not in the closed curve, which means the poles have to be extracted or skipped or removed. Hence, we will do same. Now, when z equal to 0, we have here, so this is where we have a point of discontinuity. And then when z equal to 1, let's say we have 1 here. This is just, of course, remember, this is just a simple diagram. What this means is that the range of values for the modulus will be split between 0 and 1 and from 1 to infinity. So it means the region of validity would be 0 less than absolute value of z less than 1, and you would have 1 less than absolute value of z less than infinity. This would be the two regions of validity covered. Now, this is what happens when the question does not provide a permissible region for you. But imagine if the question told you to evaluate or find the Laurent series within the region bounded by absolute value of z equal 10, for instance. If you have absolute value of z equal 10, it would mean that both of these regions would match, because you have z less than 1 and then you have z greater than 1. That is still less than 10. But what if what you have does not cover both regions? What if the permissible region you are given does not cover both regions? In that case, you would only have to stick to the parts of the region that falls within the permissible region. So those are very, very important hints to have. It plays much more important role when it comes to the calculus of residue, as we would see later on. But for now, let's proceed. We'll take the first region. For 0 less than absolute value of z less than 1, how do we evaluate this? Remember, this would mean that absolute value of z is greater than 0 and absolute value of z is less than 1. This is what this would be. Now, if this is the case, what it immediately means is that how you split off your partial fraction will be affected. So when you have 1 divided by z into z minus 1 in this region, because z is greater than 0, because it's just 0, you have minus 1 divided by z, that is untouched. But now that you have z less than 1, this part would immediately mean that 1 minus absolute value of z is greater than 0. So it means that if you have z minus 1, the denominator is going to be a negative result, because absolute value of z is less than 1. So there is no value of z that you can put here that will turn this into a positive result. So it's going to be a negative result. So what do? We have to factorize our minus so that we can change this into minus 1 divided by 1 minus z. And now, because 1 minus absolute value of z is greater than 0, it means that 1 minus z will definitely be a positive denominator. Remember, as always, the goal is always to have a positive denominator at all times. So from here, we just apply our series summation. So your geometric series comes in here. In this case, the first term is 1, and then the common ratio is z, which is, of course, less than 1. So you see why this is important. So you have this to be summation, right? You could start, in this case start from 0 to infinity, right? And you have z raised to the power of k. And that's what we're going to have, 0 raised to the power of k. So from here, we can easily see that, oh, okay, this process basically simplifies this into series notation. And then you could decide to combine this. So from here, you would have that, of course, this is a representation of 1 divided by z into z minus 1 for the region 0 less than absolute value of z less than 1. Now, what you notice is from here, you would see that immediately this part will be the analytic part, and then this part will be the only member of the principal part. So this is the only member of the principal part, where these are the members of the analytic part. So you would see that the Laurent series will change based off the region of validity you use. So this is for the first region. We'll then move on to calculate for the second region that we have here. But before you move on and see our solution for the second region, take a pause and try to solve for the region 1 less than absolute value of z less than infinity. And let's see what exactly you would have, and then compare it to our results in the next bit. Let's get to it. So now for 1 less than absolute value of z less than infinity, remember that this would imply the absolute value of z is greater than 1, and because absolute value of z is greater than 1, that would immediately mean the absolute value of z is greater than 0. So in this case, it means that our partial fraction will not need to change. It would remain as it is, plus 1 divided by z minus 1, because both denominators are positive. Because absolute value of z is greater than 1, it means the absolute value of z minus 1 is greater than 0. So z minus 1 is definitely going to be greater than 0. It's going to be a positive denominator. Now, in order for me to be able to write this as a series, I will need to factorize out z, because remember, for my geometric series, I need to be able to start from 1 in this place. So I have 1 over z coming out into 1 divided by 1 minus 1 over z. This is what I'm going to have. Now, if this is the case, I see that this is simply going to be minus 1 over z plus 1 over z summation k starting from 0 to infinity 1 over z raised to the power of k. This is what I'm going to have. Now, if this is the case, I realize something very, very interesting. And what is interesting is the fact that if I take the first term, which is k equal to 0, out of this, where k equal to 0, the first term will be 1, and then multiplied by 1 over z, it means I'm going to have plus 1 over z, then plus whatever is going to be left. And what is going to be left? We're going to have 1 over z summation k starting from 1 to infinity 1 over z raised to the power of k. This is what I'm going to have. Now, this will cancel out. These two terms will definitely cancel out just as we want. And then we would immediately have that if they cancel out, the terms of the terms left within our process would simply be, we would have 1 over z can multiply into this. So we have summation k starting from 1 to infinity of 1 divided by z raised to the power of k plus 1. And this is what we have. So we see that minus 1 over z cancels out the first term, which we have brought out, as I said. And then whatever we have left is going to be this. So what this immediately shows us is that we can immediately see that for the second region, absolute value of z greater than 1, we only have ourselves the principal part. We only have ourselves the principal part. There is no analytic part for this question. And this is very, very interesting. There is no analytic part for the question at all. Another thing that is also very, very interesting to keep in mind or to note is that you will realize that when you sum up the series form in both regions, you would have the series notation from k starting from minus infinity to plus infinity, right? Because if you notice, the first one we did, we had just one part of the principal part. This is when k is equal to 1. Now, when we come here, you'll see that this is where we said k equal to 1 here, we have z squared, which is 1 over z squared. So you see that we already have minus 1 over z here, and so that is why the z term cancelled out here, because it was not meant to exist in this region, because it already existed in the first region. Similarly, the analytic part here existed, and so it was not meant to exist in the other part of the region. Now, this is a simple fraction that is easily expressible or expanded, but then of course we still have other kinds of partial fractions that will not follow such simplicity in terms of how best to expand them, right? We'll be looking at something similar in the next video as well. As always, make sure to like, share, and subscribe, and turn on notifications so you do not miss any of our videos.